Use induction to prove that for all natural number n greater than 0, so n greater than or equal to 1, Pn is true, where P of n is 1 over 1 plus 1 over 4 plus so on plus until 1 over n squared less than or equal to 2 minus 1 over n. So this formula P of n can be written as 1 over 1 square, 1 over 2 square, 1 over 3 square, plus so on until 1 over n squared less than or equal to the right hand side. So we need to prove it for all natural number n greater than 0. So the smallest case is n equal to 1. So our base case is n equal to 1. We need to show that P of 1 is true. So P of 1 is you go from n up to 1. So we stop right here. So the left hand side of P of 1 is 1 over 1 square. The right hand side is 2 minus 1 over 1. So this is equivalent to 1 less than or equal to 1. So this is true. Now we do the inductive step. Let n be a natural number, n at least 1. So because of case n equal to 1, we already consider. So now let n be arbitrary but fixed. So thus n is at least 1. We suppose that P of n is true, meaning that this is true. We call it inductive hypothesis. We need to show that P of n plus 1 is true, meaning that P of n plus 1 will go up to n plus 1. So 1 over 1 square, 1 over 2 square, 1 over n square, and then we go one step further, 1 over n plus 1 square. The right hand side, when we see n, we replace it by n plus 1. So less than or equal to 2 minus 1 minus 1 over n plus 1. So this is P of n plus 1. Now we need to prove this inequality. The left hand side of P of n plus 1 is this sum. We know that the sum of the first n terms is less than or equal to 2 minus 1 over n because of the inductive hypothesis. So the left hand side of P of n plus 1 is less than or equal to the first n term less than this number plus the n plus 1 terms. The equality is true because of inductive hypothesis. Okay, now we need to show that this number less than the right hand side, right? One way to do it is we just need to check whether this is true by verification. So this number less than or equal to this number, meaning that we move everything to the right hand side, right? So 2 and 2 cancel out. Minus 1 over n plus 1 is here. So here we have minus 1 over n. Put it to the right hand side, we have plus 1 over n. Plus 1 over n plus 1 square. Put to the right hand side, we have minus 1 over n square. N plus 1 square. So this is equivalent to this one greater than equal to 0. So we just move everything to the right. Okay, this common denominator is n times n plus 1 square. And the numerator is n plus 1 square minus n minus n times n plus 1. The denominator, this one is greater than 0. Therefore, we can just multiply both sides by this number. So we have this one, the denominator is greater than or equal to 0. And this means that n plus 1 square, meaning that n squared plus 2n plus 1 minus n here, and minus n squared plus n, so minus n squared minus n. And this means that 1 greater than or equal to 0, which is true. And therefore this is equivalent to something always true, equivalent to 1 greater than 0. Therefore this one is true. And therefore left hand side is less than this less than the right hand side. So we have left hand side less than the right hand side, less than or equal to the right hand side of P of n plus 1. So we did prove that this is true. So therefore P of n plus 1 is true. By principle of mathematical induction, we know that P of n is true for all n greater than 0. So we are done with this proof.